Welcome to part 2 of our lesson for today. So part 1 was all about graphing exponential functions, and we did that by identifying each function's base and any transformations that came with that function. Then we had these three major, or these big three coordinate points that we plugged into and adapted, and then from there we graphed. So then the second half is going to be very, very similar to this, except instead of graphing exponentials, we'll be graphing logs. Now there is a very clear reason why I'm putting both of those together, and it's written up here on your very first slide in blue. Log graphs are similar in shape. They are a reflection over the line y equals x. Okay? And the very first lesson that we did in chapter 3 was involving taking a function, flipping it over the line y equals x, and getting a new function. And those were called inverses. And if you recall, inverses, the way that you get an inverse from another is you can either flip it over the line y equals x, you can figure it out algebraically by swapping the x and y variable and resolving for y, or your third option is you can take the original function's coordinate points and swap the x and y values and regraph. That is exactly what we are going to be doing with graphing logarithms. Okay. So a couple things I want to point out to you. This is the most basic version or format of a logarithm, and it is read f of x equals log base b of x. Okay. And now keep in mind, a logarithm is the inverse of an exponential. So if you're asking what in the world does it even mean to take the log of something, you're doing the inverse of raising something to a power. Okay. Again, that is read f of x equals log base b of x. Well, this one is very clear, and where the base is, it's that sub number. In this way that it's written, it's that sub b number, or letter in this case. And so, just like we did with exponentials, the first thing that we did was we would say, what's the base? We're going to do the same thing with logs. What's the base of this logarithmic function? Well, the base here is b. It will typically be a number, obviously, so that we can actually graph it. Okay. Then we'll do the same thing, the same step that we did with exponentials as we will do with logs. Is there an a term? Is there a c term? Is there an h term? And is there a k term? All of those rules are going to be the same. We'll take a look at the location of where a and c and h and k will be in a logarithm, but the rules are still the same. So a is going to represent a vertical stretch or flip, c is going to be a horizontal stretch or flip, h is a horizontal shift, k is a vertical shift. And then when I said earlier, inverses, you interchange or you swap the x and y values. So those big 3 points that we had for exponentials, 0, 1, 1 base, and -1, comma, 1 over the base, we're going to swap the x and y values of those, and that will be our 3 key points for logarithms. So our key points for logs are 1, comma, 0, base, comma, 1, and then 1 over the base, comma, -1. Okay. And in this picture, I've just got a graph here for you so that you can see what these two look like as inverses. So my exponential function is f of x equals base 2 of x, or base 2 to the x power. The inverse of that would be written as log base 2 of x. Okay? And so the exponential graph is in blue, the logarithmic graph is in red. Okay? If you need that visual, the graph of y equals x is right here in the gold or the orange, and you can see pretty easily, that graph's not very pretty, but you can see very easily, even with a messy graph, how it's reflected over the line y equals x. So these are definitely going to be inverses of each other. Some of the things that you should initially and immediately recognize is when they're reflected, that's going to change some things. Inverses are going to swap the x and y value. So exponential functions had a horizontal asymptote of y equals something. So then a logarithmic function, swap that value, it will have a vertical asymptote of x equals something. Okay. And so what I just said about there being a vertical asymptote for logarithmic functions, that's down here in purple, and I'm underlining it in that green. Okay. So every logarithmic function will start out with a vertical asymptote of x equals 0. Remember, asymptotes are equations. X equals 0. Unless we have a vertical shift or some type of vertical transformation that changes it from x equals 0. Okay. This is your standard format of a log with all the possible transformation parts. So I would encourage you to pause the video and write down that standard format boxed out in gray. If you need to write those 4 transformation rules again, then now's the time to do that, but I'm not going through those again. We've already covered that in a previous chapter, and we quickly reviewed those in the part 1 lesson for today. So pause this video and write down what you need to, and we'll keep going. Okay. One last thing before we keep going. With our exponential functions, we looked at all the different kinds of bases, and one of the things that we had to introduce was the number e, which is an irrational number, meaning it never ends, but we established that we were going to round it to the nearest tenth of 2.7. Okay? And so if we introduce that in the exponential functions and graphing, then we need to address what its inverse is as a logarithm. And so this will be a new term for you. However, you will have seen it on your graphing calculators and even your basic scientific calculators. Over here in the bottom right-hand corner, you will see an equation. That equation is read as y equals, or f of x equals, the natural log of x. Again, that is read the natural log of x. Okay. Now you'll notice that it doesn't have a base written. Like up here, there's a base which will be represented as some number, like 2 or 10 or 50. Okay. But for this natural log of x, there's not a base written. That is because the natural log of x is always assumed to have a base of e. Again, anytime you see the natural log of x, there won't be a specific base written, but that's because you automatically know its base is e, or approximately 2.7. Okay. Alright, so now we'll move on and we'll practice graphing some logarithmic functions. So our first function that we'll take a look at today is y, or f of x, equals the natural log. Remember that its base is e, so the natural log, base e, of x plus 1. Okay? And so just like we did with the exponentials, the first thing that we want to do is write out what is our base, and our base is e, or about 2.7. And then we want to see, is there an a term, is there a c term, is there an h term, is there a k term? Okay. There is no a term. Okay. There is no c term. Okay. If there was an a term, it would be something times the natural log of blah, blah, blah. If there was a c term, it would be the natural log of parentheses 2x plus 1, blah, blah, blah. Okay, so we don't have either one of those, but we do have an h term of positive 1. We'll address that in a second. We don't have a k term, so we can throw it out as well. Okay. Just like with any of our other transformation rules, when there's an h term, it's backwards, so that means all of my x values are going to be shifted left 1, or every x value has to be subtracted by 1. Okay. And so my next step before I graph anything is to get my table of values with those big 3 points. Okay. Now keep in mind those big 3 points are backwards, so it's not 0, 1, okay. It's now 1, 0. And it's not 1 comma base, it's now the base comma 1. Okay. And it's not negative 1 comma 1 over the base, it's now 1 over the base comma negative 1. And again, that is because logarithms are inverses of exponentials. So we swap the exponentials x and y values to get the logarithms x and y values. Okay. So now that you've got that started, you should be able to finish this problem out, or at least get the points and graph it and fill in some of that information off to the side. So pause this video and see what you come up with. So as you are graphing your first logarithmic function, again, something to keep in mind, you have a horizontal shift left 1. Logarithmic functions have a vertical asymptote of x equals 0 to start out with. Why do I know that? Well, an exponential function has a horizontal asymptote of y equals 0. The inverse of y equals 0 would be x equals 0. Okay? And so I'm starting out with x equals 0 as an asymptote, but then this transformation tells me that's got to be bumped down 1. Okay? And so, or in this case, left 1. So my asymptote is going to be x equals negative 1. That should help us get a good visual of our graphs. And now knowing that will help us answer our domain and range and our end behavior. Okay? So our domain is going to be different this time. Our domain is the set of x values that the graph has, but it's not going to be negative to positive infinity. That's because we have a vertical asymptote. My graph can only be from negative 1 to positive infinity, and that is because of the vertical asymptote. It is restricting my x values. The smallest my x values can approach is negative 1. Now the range for a logarithm is going to be wide open typically. It's going to be negative infinity to positive infinity. Take a look at your notes for graphing exponentials and you'll notice how even your domain and range seem to swap in how they are behaving. All of your exponential functions typically had a domain of negative infinity to positive infinity. Well, the inverse of that, the logarithmic functions, the y values are going to function like that. They're going to act from negative infinity to positive infinity. Okay. Now, this is very tricky. I need you to listen and I need you to pay attention, make a good note of this. The limit as your x values approach negative infinity. So I'm going to start right here. As my x values approach negative infinity, what do I hit? I hit an asymptote. Can my x values approach negative infinity if I hit an asymptote and it gets blocked? Okay. My x values cannot approach negative infinity because they're getting blocked by that asymptote. So the answer for this limit, the limit as x approaches negative infinity of this function, does not exist. And that's because my x values cannot approach negative infinity. They're being blocked. They're being hindered. And so I can't have a limit if the x values can't approach negative infinity. Now, as my x values approach positive infinity, there's nothing keeping them from approaching positive infinity. And so answer the question. As the x values approach positive infinity, what are the y values doing? They are also increasing towards positive infinity as well. Okay. And just for kicks and giggles, I threw in your x-intercept, what coordinate point hits the x-axis, and that would be 0, 0. Pause the video, write down any questions you have. Okay. We are moving fast, but that's because it is based completely on your exponential functions in part 1 of this lesson. Okay. Our second and our last example that we will take a look at with me walking through it with you and checking the answers and talking through it is this one sitting in front of you. Y equals negative log base 1/2 of x minus 2. Okay. So the first thing we want to do is identify what the base of our logarithm is. Okay. And then from there, we want to identify any extra transformations that may have occurred. Okay. So hopefully you already paused the video and you started doing that. If not, let's pause it and let's see if you can come up with all of your transformations and how does that affect your coordinate points. So if there's a k term, great. If k is 2, awesome, but what does that mean? That means I need to add 2 to which x values or which y values, so on and so forth. Okay. So give yourself a shot at that. You should be getting very comfortable with this, and if not, I should be hearing from you sometime today. Okay. Check your answers. You should have an a term of -1, which means it's a vertical flip. All your y values are going to have to be multiplied by -1. And then you also have an h term of -2, which means all of your x values need to move right to or plus 2. So now, pause the video, write out your big 3 points using the base of 1/2 and these transformations. Once you have your points, go graph them and then fill in the given information based on your graph. Okay. Reminder that with logarithmic functions, you have a vertical asymptote of x equals 0, and then if your h term shows up, then that means you are shifting that vertical asymptote. So in this case, we shifted our vertical asymptote from x equals 0 to x equals 2. And so that should be reflected on my graph. My graph shouldn't be going past any x values of 2. I can also fill in that my asymptote is x equals 2. Okay. Here's the rest of that information. My domain, my x values do not start until 2. And it doesn't even actually touch 2 because there's an asymptote there. So it's parentheses, +2, comma, infinity for your domain. Your range is all real numbers. Now, as x approaches negative infinity, I hit a brick wall, D and E. Does not exist. My x values, as my x values approach positive infinity, my y values are also increasing to positive infinity. So that's where my answers come from for the limits. Lastly, the x-intercept, I'm getting that straight from my graph, and I'm getting it straight from those big 3 points. The x-intercept, where the graph hits the x-axis, is 3, 0. Okay. Pause the video, write down any questions you have, and contact me. There are 2 more examples in your notes, but I don't want to take up any more of your time. We are sitting right on the border of a normal class period time with these 2 combined videos. So you are free to go at this time. If you would like to stick around for a couple more examples, I am not going to talk. I am just going to write down those steps slowly. So again, if you want to hang with me and see 2 more examples for your notes, you can. Otherwise, you are free to depart. Thank you so much. Make sure you are studying these rules, because Thursday I'm going to add a bunch more rules to it, and you're going to have to know them all for your test. Peace and love, and ciao. Okay, bye.